Start with the plenary lecture by Stephane Zaleski. And I agreed my introduction with Stephane, so he could be considered as the grandfather of Jerry's and Basilisk, if you count Popinay as the father of all that activities. And the topic is about contact line modes. And interestingly, this title and this research, as Stephane told me, is associated with this place. And the reason is that 2 years ago, on 7th February 2022, Stephane did a presentation, that time online, during the pandemic, at the research seminars we are still running, in School of Mathematics. And what will be presented here is, in some sense, follow-on of that presentation. This presentation you can find on YouTube, and it's received more than 600, almost 700 views. So that is the particular for people working in hydrodynamics. By the way, if to count number of views, the second and the third one, the presentation, they are also done members or participants of this workshop. Second one is by Javier Rodriguez. It's almost between 400 and 500, closer to 500. And the third one is by our organizer, Mark Bly. So it's almost 400 views. So you can find easily that is a site on the YouTube, and there are many presentations. It's about, I don't know, so you could say for 30, 40 presentation. And now we go to the plenary lecture by Stephane. Please.
Okay, thank you. Thank you for remembering this seminar here online during COVID. I really hated Zoom meetings and online seminars, and usually you couldn't discuss anything. But something happened during this seminar. Yuli Shikmurzaev, of whom I will talk more during my talk, popped in during my seminar and very strongly contradicted our view with Yash Kulkarni. Where is Yash? Yash is not here because he's hiding to work somewhere. You know, you always have problem with your children and your doctoral children or PhD students. Sometimes surprise you, as Stephane Popinay did with all the beautiful open source software he developed. Anyway, but Yash listened to the comments of Yuli during that seminar carefully, and this seminar is in a way a reply to Yuli's comments. But he's not here anymore to reply to the reply, but maybe you will take his turn. So what is the issue here? I became interested in the contact line around the years 2000s when I started studying droplet impacts with Christophe. And you remember, Christophe, we had a big problem with impacts on solid surfaces because we noticed that there was a very rapidly advancing contact line. And José Manuel also worked on this topic. And this rapidly advancing contact line, we really couldn't model. We still don't know, in fact, very well how to model it. So I was interested in that. And then Yuli came to visit, and around 2004, our lab, so 20 years ago, and he said, I was told that you have good models for interfaces. And at the time, Jerry's was not even fully developed. So he was wrong. We didn't have the models that allowed to test his theories. And so he explained his view. Of course, for him, the contact line problem was perfectly clear. For me, during the past 20 years, it was not clear. It was actually completely obscure. Every time I stopped thinking about it for more than 2 days, I didn't understand it anymore. I didn't understand what the problem was. So part of my talk will be to explain what the problem is. And I cannot speak about everything we did on the contact line today. I would need 3 hours. But I will talk about continuum contact line models inspired by nanoscopic scale physics. So nanoscopic because, in fact, what really happens on the nanometer scale, not on the micron scale. So sometimes you talk about microscopic physics as the first principle. It's not really microscopic, it's nanoscopic. And then I will talk about falsifiability. So why do I want to talk about falsifiability? Well, this is because of this conundrum. It's really very hard to explain what we did with Yash. We're still not here, okay. But I view it as a kind of Popperian point of view. So why Popperian? Well, this is Karl Popper. Maybe some of you know him. Well, maybe mention him because we are in the UK. He basically pushed two major ideas, the idea of the open society and the idea of falsifiability. So both ideas are central to this seminar. Maybe open society doesn't seem so obviously related to this seminar, but the idea of open society, and particularly according to Stéphane Popiner, who gave a talk about this last week, the idea of open society is one of the philosophical, intellectual roots of the open source code movements. And also it is related to the idea of the republic of letters, or a republic of scientists. You know, since the earliest times, since the 17th, 18th centuries, scientists were communicating freely, writing letters to each other, visiting each other, even when they were living in countries which were at war. Now this republic of letters is under attack, now that we cannot hire Chinese students anymore because of security restrictions and because of the political events that you all know about, etc. So I wanted to mention Popper in this point of view, you know. And also falsifiability. Well, falsifiability is the idea that you never really verify theories by experiment, but you can always, because if you verify it in a certain parameter range, then maybe the theories will still not be valid in another parameter range. So maybe you verify Newtonian gravity everywhere, but near the perihelion of Mercury, you cannot verify it, and you have to use Einsteinian theory, which is then again falsifiable somehow. And so this offers interesting insight into the contact line, because I will argue that the easiest way to understand what we did is to look at it as a falsification of falsification. And I will explain that. So, but before going into this paradoxical point of view, let's have a more traditional point of view and discuss the problem in simpler terms. The problem has two subdivisions, steady motion of the contact line and steady motion. I crossed out unsteady motion because I'm not sure we'll have time to talk about it, but we will see how it goes. The problem also has two aspects, the advancing line and the receding line. And I will not have the time to talk about the receding line. What I will talk about, I will try to find what is a good mathematical model of the moving contact line. And by good, you can mean many things. And maybe to reduce the discussion, it will be a model that cannot be falsified. Okay? And given such a good model, how can it be computed assuming infinite computer power? This is, as simulators, what we all hope for. We will hope for infinite computer power. Okay? And so maybe at least when you write an equation, we assume it can be solved. So we assume the equation is true because if you had infinite computer power, you could solve it and it would predict the experiment, right? That's the idea behind an equation. The idea is not just to write an equation. It has to be an equation that has predictive power. And given such a good model, can we make computation in finite amount of time? That's, of course, the engineering question, or that's also the question that we have to answer. If we don't have infinite computer power, then we cannot make predictions, and then we have to solve this third problem somehow. I'm not able to solve the the third problem. And we are barely able to solve the second problem, so we'll see. By a model, I really mean a model that is valid at all the scales of the continuum. Continuum starts at 1 nanometer, so we have a model. It has to be a model that is computed on all these scales. And good, does it mean experimental verified? Then it will be non-Popperian. Or maybe it is Popperian, we'll see. Devoid of singularities, elegant, simple. Occam's razor, if you have two models that are equivalent and one is simpler, you will choose the simpler model, right? And leads to useful engineering usage. So, well, we'll see. So that means that if you have, for example, a very typical contact line problem like the withdrawing plate, we want to model this region at a nanometer scale, not this region, okay? That's what I'm asking for. And for that, there is a suggestion, which is the Navier boundary condition. So here's a look of Henri Navier looking a bit like a bad guy. That's why I like this particular picture. And he has this boundary condition, u is lambda du dy, so that means that the velocity penetrates into the solid. And this lambda is called a slip length, and there are measurements of it. For example, in this review by Loga, you can see, I'm just showing that to you to say that it's really a seriously measured quantity, which is often of the scale of the nanometer, sometimes much bigger. Sometimes it's below the nanometer, so that's in that case, it's marked no slip. And this leads to the classical contact line model, or standard contact line model, which is a combination of Navier slip and a manner of fixing the angle at the smallest scale. So either you say the angle at the smallest scale is the equilibrium angle, which is known from equilibrium experiment, which I didn't discuss, but you can, of course, imagine that you can do experiments to measure the static angle. Or maybe the angle at the smallest scale, still a nanoscopic scale, is given by a more complicated relation, a mobility relation. Ca is f of theta. Well, the classical model is very nice, and in fact, all you have to do once you have this model is to make measurements of the mobility relation. You make measurements of moving contact lines. You get the mobility relation, you have your model. What's wrong with that? Well, what can be wrong with that is that, for example, you measure the mobility relation on a droplet sliding on an inclined plate, and then you measure the mobility relation on a withdrawing plate or a plunging plate, and you get different results. So that is really bad, right? Moreover, it's also hard because optics don't work at a nanoscopic scale. So so how do you do the measurement? So these are difficult problems, and there is no obvious answer to that. However, there is an interesting experiment which frees you from the necessity of doing various kinds of experiments in various setups. There is this experiment, the Cortin coating setup. In this experiment, you don't need to repeat the measurement of the mobility relation for various setups. You just vary the falling velocity v, which gives you the Reynolds number here in red. By varying the velocity v, it's like changing the type of the experiment. So you have a family of mobility relations for various values of v. So we started doing that with Thomas Fulana a few years ago, and we still continue. And the reason we did this, we selected this experiment, is that's the experiment that was suggested to me in 2004 by Yuli, which I call Popperian in chief because in fact, his point of view is the point of view of falsification. He claims that using this experiment, he has falsified the classical model. So the classical model is not to be used under any circumstances, which I will show is wrong. So what do you observe in this experiment? You observe a transition at a certain critical velocity. Now it's a horizontal velocity, not the falling velocity. At a certain critical velocity, you see that the meniscus is destroyed, that several bubbles happen, and basically you lose the stable steady-state solution. And you can also look at the cut. You can look at this shape, this angle, etc. You can try to predict and measure it, and then the Popperian in chief tells us that it's wrong. The classical model is wrong. So another interesting thing here is that you can, if you can solve this model numerically, you can use macroscopic observations, like the critical capillary number, to deduce things about nanoscopic physics. You basically can use large-scale observation to deduce things that you cannot observe at the nanoscopic scale. So here are some simulations by Thomas and Yash. We are close to the stability limit. You're looking at the velocity field. You zoom closer and closer. I'm not showing you all the numerical details, but well, this is such a quality of the contact line region is difficult to reach. And sometimes you have to still be careful to avoid some destruction of the interface. And then we're going to compare it to the experiment. So this is the original data from Blake in his paper. So it shows you the dynamic contact angle, but it's, of course, it was not observed by Blake at the nanoscopic scale. This is the apparent angle at a much larger scale. And as a function of the falling velocity, and you can deduce from that a mobility relation of another kind, which gives you the macroscopic angle as a function of capillary and Reynolds. The fact that the macroscopic angle depends on capillary and Reynolds is not in contradiction with the classical model. The classical model would tell you that if you can solve the equation, the macroscopic angle is a function of the microscopic angle, which is itself given by the mobility relation. So here I have rewritten this with the mobility relation. So the mobility relation is theta of u, and the macroscopic mobility relation is a function of theta of u, but also of all the other parameters of the flow, such as the falling velocity v. So if we can, by full simulations, compute this function fb, then we can verify or falsify the classical model. So to make this work, you have to show that the macroscopic contact angle depends on the flow rate v. So if you look at this curve, it's very noisy, but you can filter it. So this pink region is the filtering of the Blake data. And so you get a kind of variation of the macroscopic angle with the velocity v. And you can say, okay, now this, if you can reproduce by simulation a function fb that reproduces this variation, then it's fine. You have proven, you have verified the classical model. But what happened is it's impossible to perform this kind of simulations. We cannot reach the nanometer with simulations. However, interestingly, Yulichik, Murzaev, and Wilson, and this is the paper they wrote, were able to reach the nanometer scale. So you say, oh, Stephane, how is it that you cannot reach the nanometer scale? And they could reach it, what, 20 years ago? Well, the reason is they used a free surface model. They didn't use a two-fluid model. But, and I will say more about that later, but the result is that they get this macroscopic angle relation. If you superpose it on the previous curve, what they get is there is no variation, almost very little variation of the macroscopic angle with the velocity v. So this is the first falsification of the, according to them, of the classical model. But it doesn't work because the discrepancy is due to a free surface model. The free surface model cannot be used here because you get at high advancing contact line velocity, you get this thin air film, which was studied by several researchers, including James Pretels. And this air film creates a pressure that is responsible for the transition. So if you completely neglect this air film, there's no way you can get the result. So here we show these two curves are not in the experimental conditions, but they show that in modified experimental conditions, our simulation do show the dependence with the Reynolds number of the velocity v. So here is another fact, the critical capillary number. Can we predict the critical capillary number as a function of the Reynolds number? And can we use this for verification or falsification? Well, back to the Blake data. If we zoom here, we see the endpoints for each set of velocities. Each endpoint is a critical point, the point where you have critical angle and critical capillary number. So you can have a kind of diagram in the capillary number and Reynolds number space that shows you where the critical capillary number is. And this is the result of experiments and simulations. The dotted line on the left is the experiment. And the black line is the experiment by Liu, Carvalho, Vandre, and Satish Kumar using finite elements. And the rest to the right are our results. So you can see that our results are at slip lengths of 900, 200, and 100 nanometers. We don't reach the 1 nanometer scale, but every time we reduce the slip length, we move to the left in this diagram. So basically, the critical velocity seems to depend logarithmically on the slip length. If we extrapolate this logarithmic dependence, we do seem to reach the experimental range. However, we're in disagreement with the simulation of Liu. And so that is, again, a question. In fact, Liu don't solve the full prime either. They represent this thin air film by a kind of lubrication theory. And so perhaps this is the reason. We don't know. Anyway, we have our results. They have theirs. And we continue searching. Hopefully, if we have infinite computer power, at some point we will be able to reach this. We're also trying to study rapidly advancing contact lines in other setups where we would reach the nanometer scale more easily. So that would be another answer. But again, the problem would be to have experiments. The third fact, that was the fact that was raised by Yuli during the seminar 2 years ago, is that the velocity field magnitude increases with approach of the contact line. So that is a really surprising fact. So to understand that, if you're in the reference frame where the contact line is steady, that is the laboratory reference frame, in fact, when you do a steady state experiment, the fluid particles which approach the contact line should slow down and stop at the contact line. So their velocity should approach zero. But in the experiment, it seems that you see the opposite. The fluid velocity increases as you approach the contact line. So this is tricky. I'm sure it's tricky for you to understand this qualitatively in your mind. So I will explain in a few seconds. But let me state first that this was the third falsification argument of Yuli. So here is a view of Yasha's simulations. And you can see here, this is the heel of the curtain coating computation. And you can see that it's colored by the horizontal velocity or by the velocity magnitude. Sorry, it's colored by velocity magnitude. So you have the fast falling flow. You have a static flow region. So this could be actually obtained by the pendant drop classical computations. And so this is actually a droplet or a pendant droplet. And here you have the fast motion to the right due to the pulling plate or the horizontally moving plate. And here you have a special region. It looks a little bit like a fan if you see it from close enough. And you see that you go from the green to the red as you approach here, so the velocity increases. Very, very close to here that you cannot see, there is a region of zero velocity, but very, very close. You cannot see it on this particular graph. Okay, so you can actually make an analogy with turbulence in pipe flows. In pipe flows, you have a viscous sublayer, and so the region where U should be 0 is a bit like the viscous sublayer in turbulence. It's a very small region. The viscous sublayer is much, much smaller than the log layer, okay? And in high-speed flow, it's really microscopic. And so maybe we could have a better contact line model by applying subgrid models as people do for practical engineering computations of turbulence. So this is a colored picture. Let's go a more serious graph. Here I plot the velocity on the interface as a function of the distance to the interface, rescaled by the local Reynolds number. And so you see on the left, you have the signature of the slip model, which implies that the velocity should go to 0. I see Yash is here, so I should say I didn't plot this. Yash plotted this. And on the right, you have the signature of a Stokes flow. So what is meant by that? The right is the signature of this fan solution that I mentioned here. And it's not really a Stokes flow. It's an inertially corrected Stokes flow. A Stokes flow will actually give you a horizontal curve. There's a theorem in Stokes flow. You have a constant velocity along the interface, but not in inertially corrected Stokes flow. So it's really inertially corrected Stokes flow that explains the velocity increase noticed by the experimentalists. So in fact, another possible explanation is the solution of Benny and Timpson, which is a solution that takes into account the curvature of the interface there. But it seems to Yash and me that it's more related to the inertially corrected solution of Varma and others. So their solution is obtained by starting with the Stokes flow solution and then using it as a first-order perturbation for inertia. So the Stokes flow solution that you get is this. So we first solve separately a wedge problem. So in this wedge problem, you have the velocity is fixed on this line, and here on this red line, you have a free surface. You impose an angle, and so you can solve for Stokes flow or inertially corrected Stokes flow in that case. And so here are the results. As you reduce the slip length, you get closer and closer to the singular inertially corrected Stokes flow solution. And you get rather good agreement between the full simulation of the Navier-Stokes with the classical model and the inertially corrected Stokes flow solution. So this is my conclusion on falsification. It's a very simple and easy to remember. Falsification is falsified. Falsification didn't work. But verification also is not quite there yet because we don't have enough computer power. So here is a longer conclusion. Too little time to discuss everything. Well, that's not completely true because I have 20 minutes left, but I will leave time for questions. The classical model may explain curtain coating data if it is not falsified. Numerics are near impossible with realistic slip length. So we do need a subgrid scale model. So maybe the wedge solution offers an idea for a subgrid scale model. So you could say that in turbulence, you sometimes have an outer solution which is a potential flow, or in a pipe flow, it's a plug flow with some turbulent viscosity. And then you have the Prandtl layer, the log layer, this orange region, and then you have the viscous sublayer. So you could have the same thing in contact line dynamics. You would have the outer solution, this green region where I said it was like a pendant droplet. So there you have gravity and surface tension, or you can have, in some cases, an inertial gravity solution. Then you would have the wedge solution, and finally the slip length scale. So the slip length scale is awfully small, so you would have to locate the subgrid model in the wedge solution region. But we don't have this model fully explicit yet. And it is valid only if your grid falls in the orange region. If your grid falls in the blue region, then there is no model. And it's valid also for a particular type of flow, that is for a rapidly receding, advancing contact line. If you have a rapidly receding contact line, what happens? But this is just to test your knowledge about the contact line. What happens if you have a rapidly receding line? Well, there is no contact line anymore. You go through the Landau-Levitt-Deregin transition, and there is no contact lines. Okay. So if you have a slowly moving contact line, then you can make also various kinds of expansions. And then the problem is very different. The problem of a subgrid model for a slowly moving contact line is very different from the problem of subgrid solution for a rapidly advancing contact line. So I said I didn't have time to talk about the receding line, so I will not talk about it too much. But for the receding line, there is a very good model due to Legendre and Maglio that uses the Cox-Voynov theory to devise a subgrid model. But we don't know whether any of these models are valid for unsteady flow. And this is a problem, so that's how I'm going to occupy the remaining time. So beyond the classical model, I suggest another type of model, which is the generalized Navier boundary condition. So this condition is quite hard to understand. I mean, the first time I saw it, I couldn't make heads or tail out of it. Suppose you put the right-hand side to 0. The right-hand side, then you have the classical model. You have the Navier slip model. Suppose now you put the left-hand side, forget the left-hand side, and look at the right-hand side. What is this strange difference of cosine with this f epsilon function? Well, the cosine theta ek, it also will combine with sigma by Young's relation to give you the solid liquid and the solid air surface tensions. So this is actually an energy balance. If you forget f epsilon, this term actually means an energy balance. This is the energy gained by moving the contact line. And f epsilon is a kind of smoothing function. It's a kind of smooth delta function that is inspired directly and historically by diffuse interface or phase field models, and which were in turn directly influenced, in this case, by molecular dynamics. So there's someone, I didn't mention this slide, which is T.Z. Kian, who did a beautiful derivation of this using Onsager's theory of dissipation. Or the principle of virtual work if you want to do classical continuum mechanics. And so this is very significant. There is another trend of ideas in the generalized Navier boundary condition, which is due to Tony Lelièvre, who is a famous author in molecular dynamics. And Tony Lelièvre uses a real delta function instead of f epsilon. But the problem is you make numerical computation for a real delta function, and then it's a bit strange. As you reduce the element size goes to 0, the delta function becomes more and more singular. So what the Tony Lelièvre version of the GNBC does, the nickname for that is GNBC, of course, is that it only forces theta to go to theta ek. So it's only a numerical trick to force the angle to be equal to this equilibrium angle. So this is not a new model anymore. It is just a classical model under another guise. And you could say it's not a convergent model because the angle you get changes a little bit as you refine your grid. Yes?
Something which is puzzling me is that maybe for me it depends on the boundary condition. So then what is the boundary condition
Excellent question, excellent question. So this is the slides of another talk, but I'm going to explain this with hand waving. Thomas Fulana invented something that he called the free angle model. And Iash has also used it. So what is the free angle model? You don't impose the angle anymore as a boundary condition, but instead, you use the reconstructions, the volume of fluid reconstructions away from the contact angle. You fit this through a parabola or a circle, whatever, or you extrapolate at second order, or now Thomas does it at third order. You extrapolate back to the contact line. So now theta is the extrapolated angle from the interior. So free angle is not quite the right expression. The angle is not free.
In that case, some people could define the apparent angle.
It's a kind of apparent, extrapolated apparent angle, or it can be, we call it now the flow evolved angle, because you don't need an angle boundary condition. You have to realize that kinematically in continuum mechanics, you have lots of flows which don't have surface tension and don't have a contact angle. For instance, you have a granular flow, there is no surface tension, so the angle is whatever you observe it, is whatever is reached by the kinematics. So basically, it's the flow that evolves the angle, so we call it the flow evolved angle. Okay? And then the boundary condition will change the flow, and then the flow will make the angle relax to the equilibrium. So that's how it works. That's answer. So it's a good question by Christophe. The angle theta here is the flow evolved angle. And there is a paper on this flow evolved angle which is half published. It's like a Schrödinger cat of papers. It has a DOI, but it doesn't have an archive. You can find it on Zenodo. And so Navier looks very happy, like a general, because now he has a better condition. And if we investigate his condition, well, I just rewrote what was on the previous slide, and then I expand near 0, so the f epsilon of 0 is 1, or 1 over epsilon, and then I get this relation, and this combination, lambda over mu epsilon, is sometimes known as the contact line friction. It's the amount of energy dissipated by the motion of the contact line. It's an experimentally measurable thing, okay? And so we have this new kind of mobility relation which is predicted by the GNVC. However, if the contact line moves in an unsteady manner, then du dy is not 0, and du dy is somehow related to theta dot. So that is hard to see, and that requires a lot of discussion, which I don't have the time to give. But basically, you can imagine that in a rotating flow, you have a du dy, and also you have obviously theta is moving, is changing in a rotating flow. Okay, theta dot is the rotation speed. And so to investigate that, and also for technological reasons, the group of Jacques Simchen, Junichiro Shiomi, collaborating with Gustav Emberg and me, have set up an experiment on flexible monolayer. So this is real contact line engineering. You have these very complicated substrates, and you make the contact line move on this substrate by vibrating a droplet. So now we are into the unsteady prime, which I promised I would say a few words about. And so you have silicon and PDMS, which give very different results of different roughness, etc. So you see both the contact line velocity and the dynamic contact angle. And you can see that, at least on the apparent scale, you have no connection between the two. You actually can plot the one as the function of the other, and it's not a single curve. It's what we call dynamic hysteresis. You have this hysteresis loop that you can see. But if you shift, you create a relaxation time shift then you can superpose the curve with a time shift of a bit less than a millisecond. But the time shift is not the same for various substrates, so there is a mystery there. Why do various substrates obtain different time shifts? So the time shift, it turns out, can be explained by the GNBC. Here is the GNBC with the rotation speed, and if you can expand this, and it can be transformed into a retardation equation. So if we suppose a very simple retardation, replace u of t by u of t minus tau, and we use the experimentally observed values of t, of u, and the experimentally observed values of the angle, we have a very cheap GNBC. It's a GNBC that does not require computation, and it gives you this result. So it's good because it explains hysteresis, but it's very bad in terms of comparison to the experiment. What it means is that the angle is not predicted correctly because you probably have the wrong value of the contact line friction. But this is work in progress. There is another condition I have to mention because Christophe is here. We have the superslip condition, which is another variant like the GNBC, where instead of having just the first du dy term, we have a second derivative, and that is actually giving also good results for some problems. And that's the end of my talk.
Thank you. We have enough time for discussions and questions. Any questions, any discussions? Yep.
Thank you. So in your last model, you say that you don't recover the exact contact angle by the simulation with the experiment.
Yes.
But did you put the friction as a fitting parameter? Can you measure, I don't know, the slip length with this kind of experiment, for example?
There is no fitting function here. F epsilon is just a smooth delta function, so we don't.
So what do you take for beta, for example?
Beta is given by the slip length estimate. So
how do you estimate it, and can you maybe use it as a fitting parameter and use this to measure it? I would say. I'm not showing the exact solution of this model. I'm showing the solution of a cheap model obtained by time lag. But we did try to solve this model numerically, and we have a numerical premise that basically our results are horrible. So this is something that is basically all over the place. There is a numerical instability as you reduce the grid size. For very large grid sizes, the droplet is 1 millimeter. The very large grid sizes here means 10 microns. For 10 microns, it works. But if you have a grid of 10 microns, you have effective slip of 10 microns. So we have a completely non-physical slip. Okay.
So this is a real problem at the time.
Any other
there is a
questions?
question by John.
Oh, yeah, John. Yes.
Yeah. Have you looked at what the new boundary condition would do in the lubrication theory limit?
Yes. This is in the Schrödinger CAD paper that you can find online. Maybe Yash, you want to say something about the lubrication limit of the GNBC?
Yeah, we have one work published in Proceedings of Royal Society where we have used GNBC and superslip that shows that analytically we have shown they are more continuous, and that Schrödinger CAD paper numerically shows GNBC in a pulling plate problem.
About the lubrication limit. That was the question of John.
Yeah, we haven't specifically attempted, but numerically we have shown in that pulling plate problem when we are close to transition, it works better. Specifically, we haven't attempted the thin. Yeah, it's there. It's there in the introduction part of our GNBC paper. We have solved in lubrication limit and shown this eliminates the pressure singularity. So you can find it on Zenodo, but it's just a small section in paper.
Anything else? Please. Oh, yeah.
Hi, thank you very much. So as far as these subgrid model problems in the wedges, is there scope for looking at those in the unsteady case as well?
So you want everything? You want the unsteady case and
yeah,
the
of
subgrid?
course. Well, I mean, my concern, I guess the reason I'm asking the question is because you pointed out that you need a different situation for advancing and receding.
Yes.
So do you need a whole suite of these models that you patch together, and then is the tail wagging the dog?
Yes, I don't know. You know, I don't know. We have to start devising these subgrid models and try them.
3 more questions.
Thanks, Stephane. Regarding the epsilon, on numerical level, the distribution is already smooth to some extent. Why do we need to employ even a smoother delta function here?
Oh, it is not completely smooth, and even with slip, it's not completely smooth. So if you don't have the right hand side, then it's logarithmically diverging. The curvature is diverging logarithmically, so it's not completely. We still need to smooth it, and in fact, we have maybe the epsilon is larger than the grid size. So we have many grid points in this epsilon.
Anything else? May I ask a kind of general question? It would be reasonable to treat this problem, local problem, as a stochastic, not deterministic.
Yes, it would be extremely good because we know by looking at molecular dynamics that the real diffusion is due to a noisiness of the interface. So the diffusion and even the evaporation we see at the contact line level is due to the noisiness of the interface. So having a noisy simulation would be extremely interesting to improve the comparison with molecular dynamics.
Yeah.
Stochastic simulation or noisiness.
Anything else? Okay, and then a similar question, again from me. It seems that you believe that numerical calculations give the same as the nature. Why you do? How you can do this? Because I believe they're different, no?
I have you know, this is what's got me started on Popper. These kind of questions.
Okay. Thank you very much.
Yes. So it's a little bit like your question. Okay. First of all, the question was not well expressed because without experiment, that doesn't mean anything. We always have some experiments. What does it mean the phenomenon is correct? I suppose they mean that the prediction of the simulation corresponds to nature. That was your question. Well, that led me to try to re-explain the scientific method, which led me to the Popperian thinking. The physical law typically says in these circumstances, this phenomenon will occur. And it's verified by experiment. If you're non-Popperian, you believe in verification or induction, as philosophers used to call it. And after verification of the law, you don't need to repeat the experiment every time, right? You don't need to repeat the experiment every single time you want to design a car. You don't need to verify Newton's law of gravity every time you design a car, right? And for example, Navier-Stokes equations are verified by experiment. That's what we all believe, more or less. Okay. So, with everything correct, you can do without the experiment. However, in the case of the contact line, we don't know what the law of nature is. We have the classical model, which is perhaps not a law of nature. Okay, so I think I'm out of time.
Okay, thank you very much. And once again,